Hello students, welcome. Previously, from 4 lesson 3, we were dealing with bond breaking and bond formation calculations. In this lesson, lesson 4, we are going to do determination of enthalpy change, and we are going to start with molar heat of solution. So what is molar heat of solution? We can define molar heat of solution in two ways. The first way is it's the amount of heat energy evolved or absorbed when a substance is completely dissolved in water with further dilution, causing no more temperature change. Or you can say heat of a solution is the enthalpy change that occurs when a substance is dissolved in a solvent to give an infinite dilute solution. You can also say like that. Okay, next we are going to go to molar heat of solution. What's molar heat of solution? This is the enthalpy change that occurs when 1 mole of a substance is dissolved in a solvent or in water to give an infinite dilute solution. So if you know how to define only heat of solution, that means you also know how to define molar heat of solution. Let's repeat again. If you want to define heat of solution, you can say this is the enthalpy change that occurs when a substance is completely dissolved in water with further dilution, causing no more temperature change. So if you want to change this into molar heat of solution, you only add some small information like 1 mole. So you say this is the enthalpy change that occurs when 1 mole of a substance is dissolved in water with further dilution, causing no more temperature change. That's how you can define. So let's go examples, calculation concerning molar heat of solution. Okay, number 1, we are told on mixing 0.83 grams of potassium iodide with 50 centimeter cube of water, the temperature drops from 25 degrees Celsius to 24.5 degrees Celsius. For stop in bracket, we have been given a specific heat capacity which can be written SHC to be equal to 4.2 kilojoules per kg per Kelvin. The density of the solution is 1 gram per centimeter cube. Then we are told RFM of potassium iodide Ki is 166. So determine the first, we are told A, the enthalpy change for this reaction. So we are supposed to calculate enthalpy change of a reaction. So if you want to get enthalpy change of a reaction, we have the formula. Remember, enthalpy change is written delta H. So enthalpy change is gotten by MC delta T. So what is M? This is mass of the solution. And if you want to get mass of the solution, you only check the volume of the water dissolved or given. In our case here, we are given 50 centimeter cube of water. So that will be the mass of the solution. Remember, in the bracket, you have been given the density of the solution. So you can get the mass of the solution by just using the formula. If you want to get mass, the formula is you just have volume times density. So the volume here given is 40 times the density is 1 gram per centimeter cube. So we are having 50 centimeter cube times 1 gram per centimeter cube. That means centimeter cube will go with centimeter cube. Here we are going to get 50 gram. Okay, that will be your M. C is the specific heat capacity, and during the exam it is given 4.2 always. It will be given in the bracket. So lastly, delta T, this is temperature change. So this temperature change, we are going to use the formula as initial temperature minus final temperature. This is the formula that we are going to use when we are looking for the delta T. That's the temperature change. Okay, so you can make this gram to be kg by just dividing by 1000, so that your enthalpy change will be in kilojoules. If you don't divide this 50 kg over 1000, that means you are going to get your answer in joules. You are going to get it in joules. Okay, let's move. So we are going to go to say enthalpy change. Enthalpy change will be equal to MC delta T. So we are going to start first of all getting our delta T. What is our temperature change? Our temperature change here will be 25, that's the initial temperature, minus 24.5, which is our final temperature. Here we are going to get 0.5 degrees Celsius. Next, we are supposed to get our mass, and here mass is given by volume, which is 50, times the density of water is 1, which is given. So here I'm going to have 50 gram. Okay, so I can use my formula which is enthalpy change, will be equal to mass, which is M here, which is 50, times C, which is my specific heat capacity, and it is 4.2 here, times 0.5 as my change in temperature or temperature change. So I have to divide all this by 1000 so that I convert this gram into kilograms, so that my enthalpy change will be in the units of kilojoules. So if I calculate this, I'm going to get 0.105 kilojoules. So remember that K is small letter, J is capital letter. That is my answer in the first A. So in B, I'm told the number of moles of potassium iodide. So we have done mole in form 3. Then the formula of getting moles was mass over molar mass. So moles can be gotten by mass over molar mass, or RFM. Here we are dealing with potassium iodide, which is a compound. So we are going to use its relative formula mass. So the mass is given 0.83 gram here. So we are going to have 0.83 divided by the molar mass, or the RFM, which is given 166. It is there in the bracket. So if we do this, we are going to get 0.005 moles. Okay, thereafter we are going to go to molar enthalpy change for the reaction, the molar enthalpy change. Remember, this number of moles produces this amount of heat. What about 1 mole will give us the molar enthalpy change for this reaction? So we are going to say 0.005 moles gives 0.105 kilojoules. So we say, what about 1 mole? So here we are going to cross multiply. We are going to have 1 times 0.105 divided by 0.005. So here we are going to get 21.0 kilojoules per mole. So this will be our answer. That means the molar enthalpy change for the reaction. Okay, we go example 2. In example 2, we are told on mixing 2 centimeter cube of sulfuric acid with 98 centimeter cube of water, the temperature of the resulting solution rose by 4.5 degrees Celsius. So we are told assume density of sulfuric acid is 1.84 gram per centimeter cube, density of solution is 1 gram per centimeter cube, percentage purity of sulfuric acid is 98%, comma, then we're having that specific heat capacity, which is written C, is equal to 4.3, close bracket. So we're told determine the molar enthalpy change for the solution, including the energy level diagrams. Okay, here we are going to do the same. First of all, we are supposed to have our formula for calculating that enthalpy change. It is MC delta T. So it starts with mass of, first of all, the volume, or the total volume of solution. Total volume. So total volume of the solution here, we are going to have 2 for sulfuric acid, the volume of sulfuric acid, plus 98 centimeter cube for the volume of the water. Here we are going to have 100 centimeter cube. So from here we can get again the mass of solution. So how are we going to get the mass of the solution? That we are going to have the volume, then we are going to multiply by 1 gram per centimeter cube. So here we are going to get 100 gram. Okay, there. Next we are going to get the temperature change, but they have already given the temperature change. So the temperature change here is 4.5. It is 4.5 degrees Celsius. So let's go back to our initial one. Like when we are getting 21 kilojoules per mole, we are supposed to write, first of all, it is sign here, whether it is positive or not. That one will give us now the temperature change. If it has dropped, that means we are going to give a positive sign. If it has rose or risen, we are going to give a negative sign. So the temperature drops here. So that means we are going to have a positive 21 kilojoules per mole. Sorry for that. The next we are going to come here. The temperature change is 4.5. So we can go directly to the formula. Enthalpy change is given by MC delta T. So in our case here, our M is 100 times our C is 4.2. Then our temperature change is 4.5 given there. So 4.5. So we say divided by 1000 so that we convert our enthalpy change into kilojoules. So in doing so, we are going to get 1.89 kilojoules. 1.89 kilojoules. So then next step, we are supposed to get the number of moles of this sulfuric acid. But remember, they have given us the volume of sulfuric acid. We are not given the mass of sulfuric acid. Remember, we have only 2 centimeter cube of sulfuric acid, as you can see there, 2 centimeter cube of sulfuric acid. So what we are going to say, first of all, get the mass of sulfuric acid. Mass of sulfuric acid. So how are we going to get the mass of sulfuric acid? By having volume, which is 2 centimeter cube, then we multiply by the density of this sulfuric acid, which we have in bracket as 1.84 gram. 1.84 gram per centimeter cube. That means centimeter cube will go with centimeter cube. Here we are going to get, if you put it in the calculator, we are going to get 3.68 grams. But here, all of this mass of sulfuric acid is not pure, because we have been given percentage purity as 98. So we are going to deal with pure mass of sulfuric acid. Pure mass of sulfuric acid. So that we are going to get 98 over 100 times the mass, which is 3.68. Here we are going to get 3.6064 gram as the pure mass of sulfuric acid. So if we have now the mass of sulfuric acid, we can get the moles of sulfuric acid. Remember, moles is given mass, that's 6.0664 divided by the molar mass. So the molar mass of sulfuric acid is 98. So it has not been given in bracket, but we can get that by just having how to write sulfuric acid. It's written H2SO4. Then that means 1 times 2 for hydrogen, plus 32 for sulfur, plus 16 for oxygen times 4. This will give us now 98. Okay, when we take this mass, we divide by the molar mass, we are going to get 0.0368 moles. Okay, thereafter, we are going to say this number of moles produces this amount of energy. So what about 1 mole? So we are going to say 0.0368 moles produces 1.89 kilojoules as energy. So what about 1 mole? So we are going to cross multiply. Okay. So we are having 1 times 1.89 divided by 0.0368. So here we are going to get 51.36 kilojoules per mole. Then let us know the sign that we are going to have, whether it is positive or not. We are going to check that by the temperature. Has the temperature dropped or it has raised? So the temperature of the solution rose by 4.5. So if it rose, that means, or if it rises, that means we are going to have a negative enthalpy change, because that is an exothermic reaction. Next, we are going to proceed to drawing the energy level diagram. So I don't have a space, sorry. So I'm going to draw the energy level diagram here. So when you are drawing energy level diagram, you are supposed to have your 2 axes, that means the x-axis and the y-axis. In the x-axis, we are going to write, first of all, the reaction path. This is where we are going to have the reaction path or pathway, and here we are writing energy. We are going to write energy, which is measured in kilojoules. So this is an exothermic reaction, and we say in an exothermic reaction, that means the reactants are having a higher energy content than the product. So the reactants are sulfuric acid and also water. Sulfuric acid, which is liquid, plus water, which is also liquid. So when they are going to react, we are going to form now sulfuric acid solution. This is aqueous. So that means the air will come from the reactant going towards the product, and the enthalpy change here will be negative. So we have gotten the answer as 51.36. So 51.36 kilojoules per mole. So this is how we are going to write or to draw or to sketch the energy level diagram, because the question demands your tool including the energy level diagram. So we're done with that. We go to question 3. So in question 3, we are told when 8.0 grams of potassium nitrate are dissolved in 100 centimeter cube of water at 20 degrees Celsius, the temperature drops to 14 degrees Celsius. So what is the molar enthalpy change of the solution? So these two steps are one and the same. First of all, we are going to start with getting the mass of the solution. Mass of the solution. Mass of the solution is given by volume, which is 100 centimeter cube, times the density of the solution, which is 1 gram per centimeter cube. This one will give us 100 gram of solution. So go to the formula. Enthalpy change is given by mc delta T. So what is our M? It's 100, times our C is specific heat capacity. It is 4.2, although it's not given, but it's supposed to be given. Okay, times the temperature change, which we are told it's dropped by 14 or to 14 degrees Celsius. Then we divide by 1000 so that we make our energy in or enthalpy change in kilojoules. So we're going to get here 2.52 kilojoules. Okay, next we are supposed to get the we are going to get the number of moles. Moles is given by mass over molar mass. The mass given here is 8.0 divided by the molar mass of ammonia. Ammonia, the RFM of ammonia, let's talk about RFM of ammonium nitrate. Ammonium nitrate is written like this. So it is 2 of nitrogen, that's 2 of 14 plus. I'm having 1 times 4 for that hydrogen, then I'm having 16 times 3 for oxygen. So if I do all this, I'm going to get 80 as my RFM. So that means it will be 8.0 divided by 80 here. I'm going to get 0.1 moles. Okay, after that we say this number of moles, 0.1 moles, produces this amount of energy. That means 2.52 kilojoules. So we say what about 1 mole? So in 1 mole we are going to say cross multiply. So it will be 1 times 2.52 divided by 0.1. So here I'm going to get 25.2 kilojoules per mole. So I ask myself, has the temperature dropped or it has raised? If it has dropped, I will give a positive sign. If it has raised or rose, if I see a word rose there, I'm going to put negative. So here it has now dropped. That means I'm going to have a positive 25.2 kilojoules per mole. So I'm done with that. We are going to go to part B of the question. We are to draw the energy level diagram for this reaction. So as you have seen earlier, here we are having an endothermic reaction. To draw the energy level diagram, we are supposed to have our 2 arrows. First of all, axis, we have the 2 axes. Then what have we said about the energy content in the reactant side and product side when you are dealing with an endothermic reaction? First of all, let's label. Here we are having reaction pathway, or we can write reaction progress, and here we are having energy, and this energy is measured in kilojoules. So we said in endothermic reaction, the reactants, the products are having, we are dealing with the products are having higher energy content than the reactants. That means reactants are placed on this side. So the reactants here, ammonium nitrate, which is solid, dissolved in water, which is liquid. So we're going to get our product as ammonium nitrate solution, which is aqueous. Then the arrow comes from the reactant going to the product side, and the enthalpy change here will be a positive 25.2 kilojoules per mole. So that's how we are going to do that question. We go question 3, question 4. That was question 3. So question 4, we're having part A. We are told the heat of solution of sulfuric 6 acid is in water is negative 71.0 kilojoules per mole. Write the thermochemical equation for the dissolution of that sulfuric 6 acid. So we're having our equation as sulfuric 6 acid, which is liquid. Then we're having water, liquid. We are going to get hydrogen ion, aqueous, plus hydrogen sulfate ion, which is also aqueous. And the enthalpy change here for this solution, the solution of that sulfuric acid, this is negative 71.0 kilojoules per mole. So what is a thermochemical equation? Is an equation that has an enthalpy change or a heat change. So given that the molar mass, the molecular mass of sulfuric acid is 98, we are told to calculate the rise in temperature, that's enthalpy change, delta T, when 4.9 grams of the acid dissolved in water to give 250 centimeter cube of solution. We have been given the density of solution and the specific heat capacity, those two. So we start first of all getting the moles of sulfuric acid. So moles. How do we get moles? We get moles by mass of a molar mass. So the mass is 4.9 over the molar mass is 98 because it has been given. Here we are going to get 0.05 moles. Okay, that is it. So thereafter, we are supposed to get the enthalpy change. So how are you going to get enthalpy change? We are going to say 1 mole of this sulfuric 6 acid produces this amount of energy or heat change, that is negative 71.0 kilojoules per mole. So minus 71.0 kilojoules per mole. So it's not must us to take the negative. We are going to leave it because that negative is only telling us whether this reaction is exothermic or endothermic only. So what we say, what about this number of moles? What amount of heat is it going to give us? 0.05 moles can give us what amount of energy? So we're going to have 0.05 times 71.0 divided by 1. So here we are going to get 3.55, then it is in kilojoules. Okay, thereafter, this is the enthalpy change. This is the enthalpy change. So we are going to have our formula. Our formula was enthalpy change is given by mc delta T. Remember, this mass here we're having as 250. So we are going to get first of all mass of solution. Mass of solution. The volume of the water given here was 250. So that we are going to say 250 centimeter cube times 1 gram per centimeter cube. So here I'm going to get 250 gram. Okay. So that means my heat change here I'm having in kilojoules. That means I'm supposed to put divided by 1000. So I want to do that in the formula when I'm inserting the values in the formula. So here I will be having enthalpy change, which I have as 3.55 kilojoules, will be equal to 250 as my mass times 4.2 as my specific heat capacity times the temperature change, which I don't have, divided by 1000. Because this is in gram, so to put now 1000 down makes now that to be in kilograms. So to put here, we are going to have times 1000 and we are going to multiply here by 1000. So here we are going to have 3550, which will be equal to 1050 times that temperature change. So to get temperature change, we are going to divide by 1050, and here we are going to divide by 1050. So temperature change here will be 3.38 degrees Celsius. Roughly, we are going to get 3.4 degrees Celsius. So this was the rise in temperature. Remember, you are told calculate the rise in temperature, the rise in temperature. So next, let's conclude. We are told note the experimental value of molar heat of solution obtained in experiments are usually lower than those quoted in data books or in our textbooks. Reason, this is due to the experimental errors, which can result in one, we say some heat energy is lost to the apparatus. Yeah, some heat energy is lost to the apparatus, and number two, some heat energy is lost to the surrounding during the experiment. It's not accounted for the calculation. So we have two experimental errors that can result in this experiment. One, maybe you can say some heat energy is lost to the apparatus. Then next we can say some heat energy is lost to the surrounding during the experiment, which is not accounted for in the calculation. Then next we are going to go to page 4, where we are going to have the extended question. We have two extended questions. Kindly go through and see it. That's the end of our lesson. Thank you.